Hello everyone to our Open BioML Channel Club, the first one in this new year. And yeah, I'm very happy to welcome Gustav Adritz, who will talk about OpenFold. It's one of the Channel Club presentations with the highest interest, and I'm already looking forward because also OpenFold is part of the LibreFold project at Open BioML. So I'm looking forward to the presentation from Gustav. Thank you very much.
Great, thanks, Michael. So yeah, as Michael said, today I'll be talking to you about OpenFold, a project out of Mohammed Al-Qureishi's group at Columbia University, but with a whole bunch of industry collaborators, including OpenBioML, that I'll be thanking at the end of the talk. So I'm going to talk, I think, for about 40 minutes, and then I'll leave some time for questions at the end. But timing talks is not my strongest suit, I have to admit. So if you have any questions at any point, just don't hesitate to barge in and let me know. So I'll be starting with a kind of history of AlphaFold2. I'll assume very little prior knowledge since this is being recorded. And then I'll talk about motivation for the OpenFold project, what OpenFold is, the kinds of features we've implemented, and then a whole bunch of our major findings from the OpenFold preprint. I'll wrap up with some future directions, and then again, I hope to leave some time for questions. So at a high level, the task here is protein folding, which involves taking a protein sequence, a one-dimensional sequence of amino acid indices, and then associated metadata like MSAs and template structures, and then converting them into the three-dimensional structure of the protein. And in principle, the three-dimensional structure of the protein is fully determined by the sequence and its associated metadata, making this a tractable task. So insofar as a protein structure has implications for its function, this has been an extremely popular task throughout the years, and it has immediate applications in, for example, drug discovery. So progress started to be made in a major way with the release of the first AlphaFold, which substantially improved on the prior state of the art. It was one of the first kind of end-to-end large deep learn and like neural networks applied to the task, and it used co-evolutionary information and like really good precise engineering on the part of DeepMind to kind of improve on the existing state of the art. Now it was kind of far from experimental accuracy. Here it's about like 6 Drmsd at CASP in 2018, but nevertheless it produced relatively plausible structures and was an exciting breakthrough. But kind of the real breakthrough was AlphaFold2 2 years later in 2020, which kind of approached experimental accuracy for the first time. So I mean, at the time, it was kind of marketed and hailed as a solution to the protein folding problem. Since then, I think people have like kind of toned back that kind of claim, right? There are still places where AlphaFold2 fails. For example, large proteins with multiple domains. It's not very good at predicting the effects of mutations, for example. But nevertheless, here you have a fully automated end-to-end system that can produce extremely high quality structures for like the vast majority of known protein structures. And in fact, it was so good that even beyond the task for which it was trained, protein folding, or like on single chains, it has been proven like remarkably effective as kind of a submodule or subroutine in like diverse tasks. For example, it can do peptide protein docking. It can rank protein structures. And like most remarkably, in my opinion, it can predict the structures of like full protein complexes just concatenated to look like a single sequence from the perspective of AlphaFold. And actually, I'll focus on this task a little bit and more than the others, just because I think it proves a nice point here. So after the release of AlphaFold inference code in 2021, very quickly, it became known that you could just take protein complexes, stitch them together as single sequences, and then just kind of manipulate the positional embedding, like the index of the amino acids. For example, you can put like a little gap in between the two complexes. You can add a little like linker between the two complexes. And when you feed these kind of like hacked structures into AlphaFold, it predicts them with remarkably high accuracy. I'm showing you the Minkenbeck's AlphaFold gap, which is the variant that just manipulates the indices a little bit. And this like kind of hack to AlphaFold vastly outperformed ClusPro here, which was kind of the state of the art for like protein-protein docking at the time, right? Since then, AlphaFold gap and AlphaFold linker improved on the accuracy of this tool, and then variants of the tool enhanced with AlphaFold outperformed those as well. But AlphaFold Multimer, which was an extension of AlphaFold2 from DeepMind, outperformed them all. And the difference here is that these methods are not retrained, right? They just use AlphaFold out of the box and kind of hack it together in various ways. AlphaFold Multimer is basically a pretty straightforward retraining of AlphaFold2 on pretty much the same data with like minor variations. They increased the crop size, for example. They made the network a little bit more efficient. But nevertheless, I think this demonstrates the power of being able to retrain AlphaFold on like new tasks, right? Because as powerful as the base network is, and it's remarkably, surprisingly powerful, you can't really beat like training a new model from scratch on data designed for that task. And CASP 15, I think, illustrates the same point, right? Basically, the story of CASP 15, which wrapped up just last month, was that AlphaFold is still completely dominant, right? Like all of the top approaches are just like variations of AlphaFold. Many improved the, for example, sampling procedure. That was Wallner's entry. He kind of like and then manipulated dropout during inference to sample a whole bunch of different structures and then use the AlphaFold's built-in confidence metric to choose between them. But all of the top entries have this basic flavor, right? That they improved the NSA pipeline. They refined the structures better. They generated a whole bunch of different structures. Nevertheless, all of them are pretty much using AlphaFold out of the box without any further retraining. There are a couple of like minor exceptions. For example, the number one group here and the Pezzi foldings. He and I talked to him at CASP. He did fine tune AlphaFold a little bit. Granted, as I'll mention later on, fine tuning the network doesn't really have a very strong effect from the kind of the base weights that on the DeepMind release. But nevertheless, it shows he's the top performing group, and B, it shows that like we're not really taking full advantage of AlphaFold's potential, right? Assuming that the gains in AlphaFold Multimer, that's a general pattern that AlphaFold can be dramatically improved by kind of retraining it on task specific data as can be expected. We're kind of leaving performance on the table, and indeed, DeepMind was asked to produce kind of an unofficial benchmark for CASP 15. Just because the original AlphaFold wasn't performing as well as it had last time, and they found that just by retraining AlphaFold internally, DeepMind did this on kind of newer data, all the data that's been released since 2020 or whatever. They were able to kind of like match the performance of the best performing groups at CASP 15 just with a base network, just because like retraining it on this new data improved its performance. Yeah, so I think this goes to show that retrained versions of AlphaFold are kind of powerful and not currently being utilized. So independently of protein folding and even tasks in structural biology, another reason to kind of think about training AlphaFold and creating trainable components from the AlphaFold architecture is that AlphaFold is a kind of remarkably innovative network, right? Like while AlphaFold 1 was a pretty basic convolutional network, very similar to other approaches that existed at the time, AlphaFold2 is a number of like really like novel ideas that we expect on our group will transfer pretty cleanly to other tasks and other domains. For example, triangle attention is we expect it to be a pretty powerful primitive in like geometric tasks of many varieties, right? Anything involving point clouds or graphs and so on could benefit from this kind of structure. Recycling, which is what kind of lets AlphaFold 2 be run auto-regressively during inference without kind of muddying up training too much, is expected to be a pretty powerful primitive for diverse networks. AlphaFold has a really powerful confidence score, for example. It has this triangle multiplication module, which is supposed to be like a lightweight alternative to attention, right? So clearly, like there are pieces here that kind of merit being evaluated in different settings. And kind of with the code that DeepMind released themselves, this is not so easy to do. That takes us to the like kind of full list of motivations for the OpenFold project. And by the OpenFold project, I mean a trainable open source version of AlphaFold2 that kind of removes the barriers to training new variants of AlphaFold. DeepMind released the inference code and the kind of weights for AlphaFold, but they kind of omitted important training code and a whole bunch of data required to actually train the model, which kind of makes it difficult to train new variants, as we can see during CASP, for example. No one really did it. So our first motivation was to kind of understand AlphaFold2. There are many things we don't know about AlphaFold2. DeepMind didn't really, the supplement to the original AlphaFold2 paper is kind of like a beautiful document. It's really detailed. It outlines, it has long lists of ablations and so on. But many of those are focused on like kind of the inference time properties of AlphaFold2. They don't really release many like kind of details about how the model was, I mean, about the model's properties during training, right? And these are things that kind of we were very curious about. What do intermediate structures look like when you train AlphaFold? How much data do you need to train AlphaFold? What happens when you train AlphaFold on structurally and on data that is less diverse than the data that AlphaFold2 was trained on, right? These are questions that are not really obvious from the AlphaFold preprint that we would like to answer. Two, again, as I've been mentioning, we see great promise in retraining AlphaFold2 for new applications. So that was one of the main motivations for OpenFold. Three is that we wanted to kind of remove as many barriers as possible to training AlphaFold2 style models. So for example, AlphaFold2 is trained on these MSAs, right? These multiple sequence alignments that are extremely computationally expensive to generate at the scale that required to train these large and the AlphaFold2 style models. So we wanted to kind of like release all of the data required to train these models. We wanted to release good documentation for training models and so on. So we wanted to kind of make it as easy as possible for the community to train their own variants of AlphaFold2 outside of our lab. Four, this motivation is kind of deprecated now because initially the AlphaFold weights were released on this restricted license that prohibited commercial use. And again, given like the immense application, like the prospects of AlphaFold2 in industry for tasks like drug design, we wanted to kind of make AlphaFold2 available to industry. Last year, DeepMind changed the license and making it available for industrial use, which is great. So that kind of made this obsolete. And then five, since the original AlphaFold weights are implemented in JAX, we decided to write ours in PyTorch, which kind of is, for now at least, more popular than JAX. And by kind of writing our code in PyTorch, we were able to expose it to a huge ecosystem of really, really great tools that we use to make OpenFold better. So yeah, those were our kind of main motivations for writing OpenFold. So today, what is OpenFold, right? So we've written a full open source trainable reproduction of AlphaFold2, and we wanted to make it very faithful to the original. And in fact, it is so faithful, you can run OpenFold with AlphaFold2 weights and vice versa. You can run AlphaFold2 with the OpenFold weights that we've trained and released. And these are like identical down to like 4 decimal points, something I can't remember what our most recent unit tests or what the threshold is. But nevertheless, you can kind of verify and sanity check that OpenFold is actually doing what it purports to do because you can actually run it with AlphaFold2 weights. So this feature is annoying and difficult to maintain, but I think it's worth it as that sanity check. OpenFold is fast, especially for shorter proteins. So it's up to 3 times faster on really, really short proteins, but even up to like 1,100 proteins, you see a performance time improvement for OpenFold. This is on the same hardware. Basically, most of the speed up comes from, again, like software available to PyTorch programs, and the Flash Attention, for example, is a great project out of Stanford that improves the speed of attention. We have custom CUDA kernels, we have TorchScript tracing. It's a whole bag of optimizations, but we kind of went through the model. We refactored some modules to make them a little bit faster. Yeah, the results are pretty good, up to 1,100 proteins again, 1,100 sequence proteins rather. OpenFold is more memory efficient, kind of pound for pound. On the same hardware, you can run OpenFold on significantly longer proteins. So AlphaFold on a single A100 crashes around 2,500 residues in our tests, but OpenFold can be run up to around 4,700. Which is pretty dramatic given that the kind of memory requirement scales like super linearly with the input length. So this is pretty useful in our opinion. The improvements can come from custom CUDA kernels, really careful like tensor operations. We use like in-place operations wherever possible throughout the network. We refactored, for example, triangle multiplication to kind of remove excess copies of these kind of like large embeddings that are manifested in the network. And so on. And what's nice about these like speed and memory optimizations is that even though they kind of conflict a little bit, like the fastest version isn't the most memory efficient version, many of the features are kind of optional and can be tuned, right, and configurable. So you can kind of smoothly interpolate between like really fast inference for short proteins and then like very memory efficient inference for longer ones. And this is kind of like up at the upper limit of like the length of protein that AlphaFold can even accurately predict at this point, right? So this is a nice feature. We've retrained OpenFold from scratch, matching the accuracy of AlphaFold2, and then released the weights from this experiment publicly. We did that around June last year. On a like cameo validation sets, OpenFold, the most recent version of OpenFold does just as well as AlphaFold, right? Because they're trained from like different these like totally independent sets of weights. OpenFold does better on some proteins, AlphaFold does better on other proteins, which is nice because in principle you could, for example, given how accurate AlphaFold2's like confidence metric is PLDT, you could kind of, for example, ensemble OpenFold and AlphaFold to kind of get the best of both worlds, right? Because this is a protein, for example, where OpenFold gets 95 and the GDT, and AlphaFold is around like 4, 5, or 50, right? So they complement each other. We have released our parameters and alignment data for 5 million chains. So this is kind of what we use to train OpenFold. They're now publicly available. Most of the 5 million come from the kind of uniclust database used to generate the kind of self-distillation set for AlphaFold. So yeah, that's now available. You can train your own AlphaFolds on this data. We implemented new training modes. I didn't know how to illustrate floating point 16 training, but we implemented floating point 16 training in addition to bfloat 16 training and full precision training. bfloat 16 being what DeepMind used on the TPUs to train AlphaFold2. FP16 is nice, and then because you can now train OpenFold on kind of older GPU hardware, for example, V100s, having like lots of memory, but from a slightly older architecture that doesn't support bfloat 16. And even though those GPUs are slower, as I'll mention, like that's not really a problem for training kind of AlphaFold2 prototypes, at least, or like perfectly functional versions of AlphaFold2 that may not match the full performance of the final model, but are nonetheless perfectly capable protein folding models, or models for folding whatever molecule you please. And finally, we implemented more stable training. This was thanks to our partners at NVIDIA. Basically, they found that AlphaFold2 by default uses this clamping protocol for its primary structural loss, FAPE. Basically, 9 out of 10 batches have FAPE clamped to a maximum level to kind of prevent FAPE blowing up. They found that in the early stages of training, where FAPE is kind of the primary learning signal, this intervention was too dramatic, and in fact kind of nullified much of what the model was trying to learn in these early phases of training. And this caused a little bit of instability. While sometimes the model kind of converged, I'm looking at the blue curves here, sometimes the model converged very quickly to high accuracy, but at other times it kind of gets stuck at this lower plateau and only later converging to the same final accuracy. And sometimes you would have to run the model for like extreme periods of time, like this one right here, before you see the plateau, if it ever happens at all, right? The higher plateau, rather. So we basically changed that. Now, instead of clamping like 90% of batches, we clamp 90% of the samples within each batch. And we find that this kind of improves the speed of convergence. You'll notice this gap is like not insignificant. It's kind of converging to high accuracy about 30% faster. And then also, more importantly, it trains much more stably, right? So in these 20 runs here, not one of them ends up kind of falling onto this lower plateau. So those are kind of the features, in my opinion, the boring part of the preprints. So now I'll be talking about kind of what we learned about AlphaFold and its like kind of training procedure. Like how does AlphaFold behave in the kind of intermediate stages of training? So one finding is that AlphaFold2, as it trains, is remarkably good at estimating its own accuracy even before it converges to high accuracy. So what we see here is kind of PLDT values against LDT for all of the proteins in our kind of cameo validation set. And the points are color-coded by training step, right? So 0 is the model at initialization, and then we show its progression from there up until about step 5,000. So that's like very early on in training still. It's about here, right? Nevertheless, it's past the point where it kind of converges to high accuracy in excess of 0.8, 0.85 LDT. So, whoops, I think I missed a slide. Okay, I'll return to that slide later on. But even in the early stages of training, right, around step 1,000, 2,000, the model is not good, right? Like it's predicting structures with LDTs of like 0.4 to 0.6. Nevertheless, kind of throughout this process, it's not overestimating or underestimating by much the kind of quality of the structures. And this is, in principle, a pretty useful property, right? Like you could train AlphaFold for variable lengths of time and be relatively confident that the PLDT is going to be relatively accurate at any given time. And this is also remarkable is because PLDT is like just part of the model itself, right? It requires no external inputs, right? So the fact that it's kind of like PLDT's accuracy kind of tracks ahead of the model's accuracy is interesting. So this is the slide that I skipped. Basically, the takeaways here are this. So this is just LDDT over time for the main training experiments used to produce the kind of weights that we release publicly. It peaks at around 0.9 LDDT on our validation set. And we find that OpenFold converges extremely quickly, right? So in the first like 4,000 to 5,000 training steps, corresponding to about like 2,000 or 3,000 A100 hours, it converges to like 90 to 95% of its final accuracy, right? Which is nice because this enables you to kind of rapidly prototype AlphaFold models which is something we do later on in this talk. And without actually having to spend like 92,000 training steps on like a whole bunch of A100, right? This experiment was one of 44 A100s. And in fact, this was actually before we implemented our kind of training stability fixes. Whoops. So now you can expect convergence even faster than that, right? So you can train OpenFold pretty cheaply on like a pretty modest number of A100s at this point, and kind of achieve much of the final accuracy, which is nice. Additionally, we noticed that the fine-tuning step, the start of which is denoted by this dotted line, where the model is trained on larger crops and much deeper MSAs, doesn't really do much to improve the kind of accuracy of structures. Even kind of longer structures, when we filter out the shorter structures in our validation set and just evaluate the fine-tuning and the stage on these longer structures corresponding to the longer crops that the model is trained on, the fine-tuning step does less to improve accuracy than it does to kind of reduce physical violations in the structures. That's a notable effect. Like structures from like predicted before the dotted line have pretty notable clashes in places. They're a little bit, the secondary structural elements are not perfectly formed, and that changes very quickly after the beginning of the fine-tuning stage. But nevertheless, the fine-tuning stage isn't like a critical component of the training pipeline, which is important because it's by far the most expensive. This little fine-tuning stage was roughly as expensive as the entire previous initial training phase, just because the MSAs are so big and the crops are so long. This was, and the memory requirements for the stage are also much higher, which kind of restricts how and where and how you can run the fine-tuning. So moving on to kind of secondary structure, we basically plotted the accuracy of secondary structure using DSSP over time as the model trains. Note that kind of we focus on this period before 5,000 training steps as the model is converging, because performance thereafter is like relatively kind of linear. It just gradually improves to its final position. And we find that, for example, helices are kind of fully formed and are recognizable by secondary structure and detection algorithms faster than sheets. And for reasons that will hopefully become clear, we think that this is because helices are in some sense more local than sheets, which depend much more on the kind of global structure. Coils improve pretty monotonically here. This...
Stimmt nicht.
Sorry, is that a question?
Sorry.
Oh, sorry. Okay. So this is kind of like a high-level 3-state view. If you actually look at kind of more detailed breakdown of the secondary structure, including these kind of like more obscure secondary structure elements like polyproline helices, pi helices, and so on, you see that the kind of more common secondary structure elements are recapitulated very early on in training, right? As we mentioned, helices are learned first, and then structures follow shortly thereafter. And then for the remainder of training, for this kind of like long period after 5,000 steps, after which has already achieved high global accuracy, but like nevertheless continues to slowly improve, it seems that much of these improvements are coming from the model like slowly learning these kind of more obscure secondary structure elements in a staggered way, right? So one by one, it's kind of improving its accuracy on these more obscure elements, which suggests that there's kind of like 2 phases of training, right? One where you very quickly kind of capture the essence of these folds, right? You get most of the helices and sheets, you achieve pretty high GDT. But thereafter, you're kind of like slowly tweaking details and improving secondary structure elements. So this kind of like staggered like learning and the phenomenon extends to kind of scale of proteins. So what we're showing here is the accuracy of the model over time on kind of short fragments, non-overlapping fragments of input proteins. So for example, 10 here, these are short crops of 10 residues. in each of the validation proteins, and then we make them longer and longer and longer until the pink line is the kind of full protein chain. And you see that the model kind of learns from the ground up in some sense. Local and the structure, represented by these like very, very short crops, achieves high accuracy much faster than the longer crops. And in fact, there's this period here around like 2,000 to 3,000 steps where accuracy on these short crops is uniformly pretty high, right? Like if you zoom in far enough, you'll see like relatively accurate structure, but global structure still lags behind, right? Like here we have this point where like local structure is at like 90 GDT, and then global structure is still hovering around like 40 to 50, right? So in the same way that it kind of learns secondary structure elements one by one, it's also kind of learning protein folding at different scales one by one from the ground up. And this is also true for kind of helices and sheets. What we did here was we grouped helices and sheets by size, where size means kind of length in the sequence for helices and number of and the sheets for the number of threads in the sheets, in the base sheets. And you see here too that like and the smaller helices and smaller sheets achieve high accuracy much faster than the very, very long helices and long sheets, right? So across the board, it's kind of learning structure from the ground up, from local to global in a staggered way. So this is my favorite finding from the preprints. Moving on to like tertiary structure here, like what do the actual intermediate structures look like? This was one of our kind of main curiosities coming into the project. One of the reasons we wanted to make a trainable version of the model. And so in contrast to the animations in the original AlphaFold paper, which kind of show predictions evolving over multiple recycling steps, right? You can see how the protein actually kind of forms proteins during inference. What we've done here is kind of animate proteins as predicted by the model over different training steps as opposed to recycling steps. So these are the final predictions of intermediate versions of the model from step around 0 to that critical point around like 5,000 once it's already basically converged. And this is what we see. Hopefully this video works. Yes, great. So first it forms these like one-dimensional kind of rods or logs. Those then expand into two-dimensional sheets almost, which then kind of blow up like balloons to form the three-dimensional structure. Notice that this has already happened before step 2,700. Thereafter, it kind of starts to fill in the secondary structure. It pops in one by one. And that's kind of corresponds to the spike you see on the secondary structure curves in helices and sheets. So this is not just something that happens to individual proteins. It happens like pretty much across the board in our validation set. So again, it forms a log. It forms this completely flat two-dimensional structure that then expands into a three-dimensional structure. Oh, sorry, is this the same one? I meant to, oh yeah, sorry, that was the same one. This is a different protein, a base propeller. So again, you form this one-dimensional rod. It kind of expands into this two-dimensional sheet. It then kind of blows up into a three-dimensional structure. Again, the transition between 2D and 3D is extremely fast. It kind of very rapidly expands into accurate three-dimensional structure. And then from there on, the three-dimensional structure barely changes, but and in fact, it is pretty accurate, as you see, right? Like this is after the model's already kind of crested the plateau. It starts to fill in the secondary structure. Note that the color scheme here corresponds to the secondary structure assignments of the final prediction at step 5,344 or whatever, right? So it's worth pointing out that let's see if I can actually kind of capture this. This is going to, here we go. I'm going to try and just snag the second 2D structure here. You see that the secondary structure is kind of like almost visible in the 2D and in the 2D structures, right? Here you see like the red corresponds to beta sheets. So you see these like long wavy lines here, and then yellow are helices, which are kind of squiggly, almost like flattened versions of helices. This isn't the best of view. It's more obvious if you I invite you to kind of look at the animations on your own time. But it really does appear to be like a two-dimensional flat version of the final protein. So as I mentioned, this is another way to visualize the phenomenon. What we did here was kind of color proteins by the kind of extent of its extension in the direction of the principal components of the final three-dimensional structure. And the color bars here show the relative magnitudes of the principal components of the structure, which is kind of like a proxy for the flatness of the structure, so to speak, right, of dimensionality, right? So these one-dimensional structures have one large principal component, and the other two are tiny by comparison. Next, in this 2D phase, they kind of develop a second principal component. The third one is still insignificant because they are like pretty much flat two-dimensional manifolds. Then suddenly they pop into 3 dimensions. Now the principal components are like roughly evenly distributed, reflecting the fact that like the 3-dimensional protein structures are approximately spherical. And then finally thereafter, it kind of refines the secondary structure over this kind of longer period of time between 2,000, 7,000 training steps and 5,300 training steps. This is another view of the same phenomenon. This is just kind of the average eigen and like magnitude of the principal components of a whole bunch of proteins, of like all of the proteins in a validation set. And you see that the first principal component becomes large, like while the other two are still mostly like 0 or non-existent. Next, the 2-dimensional one pops in, and then very shortly thereafter, you kind of grow a third one. So there are multiple possibilities for which this could happen, right? Like the model could be forming just like pretty random 2-dimensional sheets, and then kind of scrambling all the protein and all the atoms rather, as it kind of rearranges them into a 3-dimensional structure. But we can actually make a stronger statement than that, right? The kind of 1-dimensional, 2-dimensional projections of the proteins are not simply PCA projections of the kind of final structure, right? It's not that clean. Nevertheless, they aren't kind of random assemblages of atoms either. In some sense, the flat and 1-dimensional, 2-dimensional versions of the proteins are approximate PCA projections of the final structure. So we show that with these plots right here. So what we're basically doing is taking all of the predictions across these different time steps. We're kind of sequentially aligning them to the final prediction at step 5,300. And then we're kind of measuring how far each atom moves in the direction of the final structure's principal components, right? So basically, what we see is that there are kind of 3 stages, right? One where proteins are primarily moving in the direction of the first largest principal components. Next, you have proteins moving in the second and third principal in directions of the second and third principal components, while movement in the first principal components is like is suppressed, right? It's nowhere near as large as it is in the first step, indicating that the proteins are the atoms have pretty much reached their final positions in that direction by this point. And then finally, you have a third phase dominated by movement in the third principal component. Note that there isn't always a clean separation between the second and the third principal components in the kind of second phase. And this has in large part to do with the fact that A, they're not like perfectly flat. There are like tendrils sticking up above the kind of flat surface of the 2-dimensional structure. And also, they aren't really like perfectly planar either. Like, even though they are 2-dimensional, the 2-dimensional structures are kind of like bent in some sense. They're like 2-dimensional manifolds as opposed to truly 2-dimensional structures. So in this phase, you do see some motion in this kind of like Z direction. But nevertheless, here you see like 3 pretty distinct phases of motion of atoms. So yeah, at the beginning of the 3D phase, the 2D structure is in some sense kind of correct as a 2D projection of the final structure. As another way of illustrating this, we plotted the Drmsd of the projected versions of the final protein against the predictions. So basically, what we did was we took the 3-dimensional final prediction at step 5,000 again, the same one, and then we projected at every training step, we projected the prediction into 2 dimensions and 1 dimension. And then we compared them to the 3-dimensional structure, sort of like this, right? So red here, oh, sorry, the color scheme got a little bit mixed up. This is, of course, a 2-dimensional projection of the prediction at any given time, and we're comparing it to the final 3-dimensional structure, right? So there are kind of 2 scenarios here, right? One is where the dimensions are completely independent of each other, right? The kind of quality improves in the first dimension, independently of the second dimension and the third dimension. And then there's a second scenario, right, where the 3-dimensional prediction at any given time is exactly identical to the 1-dimensional projection, right? This is kind of perfect PCA projection. In that scenario, the 1-dimensional and 2-dimensional curves, for example, would only diverge once the kind of 3-dimensional structure, the 3-dimensional prediction, grows in the second dimension, right? And what we actually observe is not like it's not perfect staggering, it's not no staggering, but it's much closer to this perfect staggering scenario, right? So up until the end of the 1D phase here, all 3 of the curves are pretty much identical, indicating that the predictions are in fact like pretty much 1-dimensional PCA projections of the final structure, right? Then when it grows, the predictions start growing the second dimension, they are identical, they are identical to 2-dimensional projections of the final structure. And then once they grow their final dimension around step, again, 2,700, they diverge from the two-dimensional literal PCA projections of the final structure and start to approach 100% accuracy as they become the prediction at 5,324, right? So you see this kind of clear staggering as it moves through the phases of dimensionality. So next, I'll be talking about our data reductions, where we trained, oh, I'm sorry, this is, I don't know why it skipped so many slides. Okay, well, this is the slide I meant to go to. I'll be talking about these data reductions that we did, but we trained AlphaFold2 from scratch on kind of subsamples of the full data set we have available to us. So the first thing we did was just randomly sample proteins uniformly, right? We took 5% of the proteins, then 10% of the proteins, and 15%, and kind of trained independent versions of the model on these tiny data sets just to see how much data you need for AlphaFold to kind of achieve critical mass, so to speak, right? Note that we did these experiments without self-distillation, right? Because we wanted no influence from the full model kind of leaking into these experiments. And we also ran the experiments without templates, in addition to with templates here, just to make sure that no like structural information seeping into the data set from via templates, right? And we find that even on tiny data sets, oh, sorry, one more caveat here is that, again, these models are only trained for about 7,000 out of 92,000 total steps, right? So these are tiny models, well, they're not tiny models, they're the same size as the original AlphaFold. They're trained on tiny data sets for very little time and without templates. And we find that the performance is remarkably robust to these ablations. The full model here is in pink. Without self-distillation, it peaks out around 0.83 LDDT at step like 20,000, 25,000, not pictured here. And you see that models trained on like 10%, 12% of the like full data set are almost indistinguishable from this full run, right? And in fact, a model trained on less than 1% of the data, so around 1,000 unique chains total, achieves LDDTs that are like competitive with those of the original AlphaFold, which was trained on all available protein data at the time, right? So really, this shows like a remarkable robustness and like generalization capability on the part of the architecture. What we then did was we expected this to kind of break the model, and then we like end it at that. But we decided to, in addition to reducing the size of the data sets, also reduce the structural diversity of the data sets. And we did this using CATH, which is kind of like a hierarchical taxonomy of protein structures. What we did was we went to the lowest, well, rather the second lowest level of this hierarchy, topology, and started ablating entire topologies, or like percentages of all the topologies that are available, right? So again, pink here is the full training experiment, and then the blue curve is a model trained on just 5% of the available topologies. And the performance, of course, is worse than when we just trained it on 5% of like chains in total. But nevertheless, you see kind of models trained on extremely like data that's extremely lacks diversity. I always look for the opposite of the word diversity, but I can never find it. Anyway, on extremely undiverse data sets, nevertheless achieves like 70 LDDT. And note that these are being evaluated on holdout sets of completely unseen topologies, right? So each of the chains in this validation set is from a unique unseen topology. This is in some sense like the worst case scenario for the model, right? Like every single protein is from a new topology that the model has never seen before. And nevertheless, it achieves like just 50% of the remaining topologies achieves accuracy comparable to the full model, which is pretty remarkable. This holds true at the next level of the hierarchy. We went up to architecture and trained models on subsets of the architectures. The 5% one here is just a single architecture. There are only 42 architectures total. We held out a whole bunch of them for the validation sets used here. And so the 5% one is just a single architecture. And nevertheless, it's able to reach 60 LDDT evaluated on proteins from like completely held out architectures, which is pretty amazing. And then finally, in our final attempt to break the model, we went up to class and just held up entire classes of proteins, right? Basically, what we did was we trained one model on the mostly alpha class and evaluated it on class 3, which is alpha and beta. And then we also trained a second model on the mostly beta class, which again is chains that contain mostly beta sheets, and evaluated on the same like class 3 validation set. And we find that again, like the model doesn't really care very much. it achieves very high LDDTs, despite being trained on very, very little data with extremely little diversity. So these models have pretty funny properties. Like we thought this was pretty comical. What we did was we took these two models here, the kind of yellow one and the red one, the alpha one and the beta one respectively, and we evaluated it on kind of like a mostly helical protein and a mostly kind of beta protein. And we find that the helical model here in yellow predictably does very well on the helical protein, right? And while the beta model kind of puts these like spurious beta sheets in the structure, the global fold isn't really exactly correct, but nevertheless, it's forming like, you know, well-formed alpha helices here, right? Like it's not a total disaster. Here again, the alpha helical model doesn't really know how to form beta sheets, but nevertheless, the global structure is still pretty decent, right? Like it's forming the beta sheets, even if the kind of the resolution of the secondary structure isn't good enough for the pi-mol to kind of render it properly, and also puts the spurious alpha helix here that shouldn't be there. And while the beta sheet pretty much gets the protein correct, right? But despite these kind of like comical examples, if you actually evaluate the model's accuracy on the alpha model's accuracy on beta sheets, for example, and the beta model's accuracy on alpha sheets, the performance is still like very, very good. And again, even on the categories where they are not trained, the gap is only something like 0.08, like F1 score, right? So the beta model is still remarkably good at predicting alpha helices and vice versa, right? So these are like perfectly capable models, like given the extreme conditions under which they were trained. So this kind of reflects again the fact that AlphaFold seems to be learning structure from the ground up, right, from local to global structure. And so insofar as the categories are kind of classifications of global structure, AlphaFold doesn't really need that, right? Like it seems to be able to learn remarkable amounts of information about protein folding just from like kind of local structure, and it can generalize that remarkably well to kind of totally unseen alien structures. One thing to note here is that, again, to illustrate that point, global structure benefits from additional dataset diversity more than local structure does, right? So this is the same data I was just showing in the ablation plots, just kind of formatted a little bit differently. Now the percentage of the training set that we use is on the x-axis, and the GDT versus LDDT is on the y-axis, right? Where GDT is kind of like a more global metric. And you can see that the gains from increasing the size of the dataset, well, the diversity of the dataset rather, are much greater for the global fold than they are for the local fold, right? Because the local fold really doesn't change much at all, right? Like small fragments. Oh, I should mention the different colors here correspond to different like fragments of different lengths, just like in the shard plot I showed a little bit earlier, right? So this is for the topology splits. And I should mention that the kind of LDT shows a much smaller gap, right? Insofar as it kind of captures. It doesn't capture global structure to the same extent as GDCTS. Same holds true for the architecture split. You see the same pattern where the kind of global structure benefits much more from additional diversity than the kind of short shards do. So future directions. We have this now kind of academic industry consortium now, the Open Molecular Software Foundation. And we are interested in kind of working on additional tasks using the OpenFold codebase and other kind of community efforts to advance, structural biology. For example, we're interested in single sequence structure prediction. We're interested in prediction of multiple conformations, and the whole family of tasks in protein folding and beyond, right? So we hope to use the OpenFold codebase and again the contributions of everyone in the community and in the foundation to kind of make progress towards these tasks in kind of like a way that benefits the community and that it is in a way dictated by the community, right? So that's it. I'd like to thank my many co-authors. Nazim was kind of equal contribution first author on the paper, and Mohammed as well, in particular Mohammed, who's kind of the PI for the project and who provided many of the nice clean graphics that I've been using today in my talk. So yeah, thank you for listening, and yeah, I'd be happy to accept or answer questions.
Yes, thank you very much for the great talk and the great slides and the nice figures. Are there questions out there?
Yes, I actually have a few questions.
Yes.
Okay. Okay. So just a rough summary of what you've done, basically, right? Like you've taken the AlphaFold, sort of like you've basically like like the some of their code was like not open source, right? And you're basically
right.
what you've done is like you've sort of like not eliminated, showing like the dynamics of how like these protein structures are being learned, correct?
That's right. Yeah.
Okay, so I have a question, right?
Oh, yeah, go ahead.
Sorry. No, I have a question, right? Like when you were showing, for example, like the ablation stuff, or like when you were saying like, like the PCA, the dimensional reduction, like first, like it was learning on one dimension, then it was learning on like the other dimensions. Are these like, like realistic modeling of like the physical processes, actual like taking place in actual physical reality when like protein folding is being done?
So no, actually, it's a very strong no, right? Like these structures that like are in these intermediate phases are extremely unrealistic, unphysical, right? And I think the fact that AlphaFold is able to form these structures is pretty interesting, right? Because prior protein folding approaches, like for example, AlphaFold1, have like much stronger like physical constraints on the structures that the model can actually output, right? So
Right.
AlphaFold1 uses this like energy and the potential to kind of like form a kind of contort the actual kind of chain of amino acids into a realistic structure, right?
Right.
And that kind of like limits the expressivity of the model, right? AlphaFold2, just at initialization, all residues are placed at the origin, right? And AlphaFold is kind of like free to put them wherever it wants, right? Without any kind of restriction. And the violation loss, which kind of enforces these chemical constraints, right? The bond lengths and so on. That's only actually activated in the fine-tuning stage, like very late in the like folding process. So AlphaFold2 seems to indicate like that removing these kind of like biases, these like hard constraints, is potentially conducive to kind of final accuracy, right? In that the model is kind of free to do whatever it wants without kind of intervention. And what it does with that freedom is kind of learn protein folding much faster than the other like methods that we've tried to apply to the problem. So yeah, it's not physical, and that might be a good thing.
Is it like sort of like almost like showing us like what sort of like evolutionary like trade-offs that has been like sort of like developed in the history of these protein folding things?
I'm not sure if I actually don't think that the kind of flattened kind of projection structures actually have any kind of basis in reality at all, right? Like I don't think at any point in evolution or the kind of actual physical protein folding process, you end up with these like two-dimensional flat proteins. Nevertheless, this seems to kind of represent like an easier path through the optimization landscape than like.
So I'm saying like, are there like optimization sort of like pathways that like just for some reason just been ignored, or like we've not reached those optimization pathways, even to these like physical?
We speculate in the paper that like incorporating this kind of pathway as a kind of physical, as like a prior, may kind of help to improve performance insofar as, for example, Sergey, soon after we released Sergey Ovchinnikov at Harvard, soon after we released the paper, he tweeted and speculated that like the model is implementing some kind of mathematical procedure that he had previously attempted to use to fold proteins with actually some success. So this may indicate that it's worth revisiting, like kind of figuring out exactly mathematically why this for example makes it easier to learn FAPE or like whichever loss function is inducing this kind of behavior.
Right.
And then designing networks to kind of do this explicitly. Perhaps that would be a kind of better approach to the problem now that AlphaFold has kind of like taught us what to do.
Okay. And to follow up on that, like, do you think like you can eventually use these methods to kind of like, like design like just better protein folding?
Yeah, I think so. Like, so protein folding like prediction techniques. Definitely, I think it's worth experimenting with kind of like hard coding this kind of progression, right? Where like you first encourage it to learn the first dimension, then the second one, then the third one. Just because like there seems to be a whole lot of circumstantial evidence from like Sergey and our experiments that like this is kind of an easy way to learn these like kind of like structural losses, like FAPE, for example, which is the one that AlphaFold uses.
Okay, yeah, thank you for answering my questions.
I have one short question because it fits now to the other question. Do you think when you kind of implement kind of more of the natural protein synthesis process that could benefit the folding, like this sequential generation of the amino acid chain, because this is where in nature when also like the folding starts to happen?
So it could be that like incorporating more like natural priors could improve, like, improve optimization and kind of help the model learn these structures. Nevertheless, I think the difference, I mean, obviously there are like 10 differences, like 10 hundreds of differences between AlphaFold1 and AlphaFold2. So it's kind of difficult to pinpoint exactly why AlphaFold2 is so much better, right? But if this kind of like additional freedom that AlphaFold has is a kind of useful property, like if that is one of the reasons why it's able to surpass AlphaFold1, which has like much more realistic physical kind of assumptions baked into it, it's a trade-off, right? Like it could be the case that giving the model like freedom to do whatever it wants kind of helps it solve problems that we don't even know exist, right? Like optimization problems are like very subtle and like may have held back AlphaFold1. Or it could be the case that we could find some set of priors that like actually does kind of help the model navigate the loss landscape and kind of learn the structures the way it needs to learn, right? So what I said before, that like it may be useful to kind of bake this into the like inference process of protein folding prediction structure or network. That's just, I'm speculating there, right? Like it could be the case that the kind of loss of freedom that AlphaFold2 enjoys would be could detract from the final accuracy, or it might help just because perhaps we were just using the wrong priors before, right? But it's hard to say whether kind of incorporating more of these priors would be a good thing or a bad thing.
Mm-hmm. Thank you. We have another question from Samar. He wonders, how much does the final physical energy minimization using empirical force field help in the training?
So the kind of force field and like the rest of the physical constraints are all baked into this kind of like violation loss, which, as I mentioned, is only activated. I can go back to the slide here. The violation loss is only activated here after the dotted line. So after the model's pretty much like completely finished training. And it does have like a noticeable effect. Like, as I mentioned, like prior to this line, you'll see like obvious clashes, you'll see like weird bond lengths and so on, right? Like there are like subtle problems with the structures at this point that the violation loss very, very quickly fixes. But this is actually one of the components of this kind of like freedom that I mentioned, right? In that DeepMind finds that when you activate the the violation loss from the very beginning, this kind of interferes with the model convergence, right? Like the model doesn't end up being as good when you have these force fields activated from the very beginning. And that may be because they would prevent the model from forming these like extremely unaphysical two-dimensional structures, right? Because if you have force fields between atoms and force it to like obey realistic distances and avoid clashes and so on, it's not going to be able to form this like two-dimensional manifold that it uses on the pathway to three-dimensional structures when left to its own devices, right? So it does help to refine the structures visibly after the beginning of the fine-tuning stage, but you don't want too much of that, is what AlphaFold seems to be telling us, right? Like that should be kind of applied as a refinement step late on in the process, as opposed to a core part of the folding algorithm. Does that answer your question?
Yeah, thanks from Samar. Great answer. Are there any other questions? If not, I have a couple of. What's your take on single sequence setups? Do you think it's in the future we will get rid of the multiple sequence alignments, or is this something that will be needed, or yeah?
So yeah, that's I'll go back to the CASP slide here. So on the one hand, kind of PLMs, which have been kind of presented as a kind of way to model these like single sequence orphan proteins, seem to kind of be lagging behind like huge MSA-based AlphaFold2 approaches, right? Like ESM here, ESM2 was the best performing PLM method that doesn't use MSAs at CASP this year, right? And as you can see, it kind of lagged behind the top entries. But I definitely think there is promise, right? Like we've actually internally been training kind of variants of AlphaFold without MSAs, without templates, and so on, and with some pretty promising results, right? Like obviously we haven't managed to reach the kind of level of AlphaFold2 yet, but I think there is promise for applying AlphaFold2 style methods to single sequence protein structure prediction. And that's a little bit unsubstantiated at the moment, but I guess stay tuned for that.
Do you think that model scale is something that could kind of be very helpful? Like,
I actually do think so. So basically, I think one of the takeaways from the ablations that we actually discuss in the paper is that there is a large literature now in language modeling, in like deep learning, about these scaling laws, right? That like if you, to train compute optimal models, there is this kind of relationship between like model size and dataset size, and kind of like they kind of scale as a power law as you increase the model and as you increase the model size and the dataset size when the model isn't bottlenecked by either of the two, right? And basically, long story short, these ablations seem to indicate that the model is bottlenecked by size, right? Insofar as the same model does exactly as well on like all of the data as it does on like 15% of the data, unless the data truly is like completely redundant, this seems to indicate that the model isn't like expressive enough in some sense to kind of capture the full diversity of the training data, right? So we expect that increasing the size of AlphaFold2 past and the kind of default size 93 million parameters used by DeepMind could see like potentially substantial improvements in folding accuracy, and perhaps that would transfer to kind of single sequence accuracy just for free, you know. So actually investigating the scaling properties and like actually kind of drawing out the scaling laws of AlphaFold is something that we're definitely interested in doing ourselves.
Do you see double descent in this kind of
yes,
scaling
actually.
laws?
So you might have spotted that right here. Very many AlphaFold, we haven't investigated this carefully at all. So like this is definitely an open question for future work. But many of our models here show weird little double descent phenomena. And anecdotally, they seem to differ based on how much data you use, as should be expected from the kind of double descent literature on language models, which may just transfer cleanly to the transformer-based AlphaFold2, right? So yeah, like there are plenty of little double descent phenomena in our experiments. How, like, what the properties of those are, like when they happen, we didn't investigate very carefully. So yeah, that's an open question. Are there any other examples here? Maybe I can find. Oh, yep, here we go. The architecture splits have them, but only the large data. No, sorry, no. Okay, so the 100% architecture split has it, and then also the 5% one. So it's a little bit hard to say. Granted, the resolution of these plots is relatively low, right? So it's possible that the green and yellow curves have just smaller double descent curve and the double descent plots here. But yeah, it's hard to say. Again, we didn't investigate this very closely.
Just another like question based on like the scaling stuff. Like, do you think like this is as efficient as you could push it, or like basically how much more efficient do you think we can make these models?
So I think I've reached the end of my own chain. Like we really like kind of poured over the models and like everywhere we made them more efficient. But like more talented like optimizers have already taken OpenFold and made it more efficient for training. For example, FastFold, Unifold are both PyTorch based implementations of AlphaFold2 based on OpenFold, but that have like very favorable properties for training, for example. And the FastFold and Unifold both have like very, very fast training times. And I think they claim to reduce training times by like 60% or something. So that plus the kind of memory efficiency of OpenFold, plus the fact that DeepMind just trained AlphaFold on like 16 gigabyte TPU v3s, right? If you're training these kinds of models on like 80 gigabyte A100s, you have a lot more leeway to kind of increase the size of like intermediate activations of channel dimensions, the number of parameters, and kind of move past the points that AlphaFold was trained at, which in my opinion was just based on the kind of limitations of the hardware at the time, right? Like I don't think there's a very principled reason why they stopped at 93 million parameters. I think it's just they ran out of memory. So yeah, so this is a like really interesting series of questions. And in fact, I'm currently working on a project where we kind of enumerate the actual scaling laws of AlphaFold2 and see how far performance can be pushed.
There's one more question by Samar. You mentioned DeepMind was requested to make a submission for CASP 15. Did they not participate in the challenge this time?
They did not participate in the actual challenge. I think they're holding out for a future competition from what I've heard. But yeah, unofficially, kind of the DeepMind, the CASP organizers asked them to kind of produce predictions using this kind of like new version of the model that they released at CASP, which is kind of like just trained on slightly more data with larger crops and so on. And they kind of, the CASP organizers use this as a kind of an unofficial benchmark for the actual and the participants. But no, DeepMind was not actually like participating at the competition. Oh, there's a chat here. I didn't see that.
Yeah, I was covering all the.
Oh, I see.
So no worries. Yeah, are there any questions left? Otherwise, I have a last one, but yeah.
Great. Sorry, Michael, you're kind of breaking up for me. I'm not really getting. I didn't get any of that. That kind of broke up.
Can you hear me? Okay. A hiccup in the internet.
No. Okay, now I can hear. Now I can hear.
Connection. Can you hear me now?
Yes, I can. Oh, but not anymore.
Perfect. If there are no questions, I have just one last. This is maybe adding another modality.
So you're still breaking up a little bit for me. Could you maybe send it in the chat, Michael? Oh, he's gone. Yeah, I guess we'll wait for him to come back. Did anyone else have trouble hearing Michael, or is it something on my end?
Sorry, can you hear me now?
Yes, I can hear you.
Okay, but the recording is also still running. Perfect. No, my last question would be like, do you see in the future the benefit of adding another data modality? Like, there's a lot of like description in text form for proteins. Is this something that you see can be used in a meaningful way, or is this more like if we want to kind of maybe query protein features with text, that this is something that is needed but not beneficial for the structure prediction itself?
Yeah, I mean, I'm sure. I mean, I'm sure that like adding additional data modalities could potentially benefit, right? Like AlphaFold2 has a whole bunch of features. You have the MSA, you have the templates, you have the sequence itself, right? Like, so I'm sure like throwing more data into the bag could potentially have benefits, right? Protein structure and the information seems to be encoded in like really strange places, like how you can take like a protein language model and like just linearly project the final like attention map to produce a plausible structure. Is one of my favorite findings from the past year. So protein structure seems to be everywhere, and I'm sure that adding more data modalities could kind of make it easy to find.
Thank you.
And again, this is now something that anyone can do with OpenFold. We have the data, we have the trainable version of the network, so yeah, you can do that kind of stuff now.
Are there questions left, or? Because otherwise, I want to thank you again. It was really a nice presentation. I really enjoyed it. I learned a lot on the way, and yeah, I'm looking forward for your scaling loss plots then, hopefully in the future.
Yes. Okay, so thanks for coming, everyone. Bye-bye.
Thank you, Gustav. Bye.